Hello folks, and welcome back to Behind Schedule and Over Budget, the show where things end up weighing a good bit more than you expected they were going to. So, in our last episode, we introduced this channel's next project, which is going to be a Wind-Up Benchy pool toy. So, what is that project going to be? Well, we're going to take the ubiquitous Benchy that everybody knows and loves, and we are going to turn it into a wind-up toy. So, let's take a look at this design from a very high level. And something we'll see as we go through this presentation is that we're going to delve quite deeply into the design aspects that are going to be involved in making this this wind-up Benchy. Probably a little too deep, but I like to break these projects down and have a little bit of fun. Again, delving deep into what goes into them. I want to learn a little something from doing these projects, and I think I learned well by getting real deep into the nitty-gritty of what's involved here. And again, if you're watching this, I hope you enjoy, kind of following along with this and maybe learning a little something too. So again, we want to make a wind-up toy, and a wind-up toy that's also a functional boat. So what does that involve? Well, we want to take our ubiquitous Benchy here, and we want to add a few major components to it. We want a way to input energy into the boat. We want something that's going to store that energy that we input, and then release that energy in a way that we can kind of time it down so that we can drive a propeller. Yeah? We have the aspects here of a wind-up mechanism and a functional boat, really. Beyond that, a couple other aspects would be nice would be to seal the boat up. Again, this is going to be in water, so we don't want this thing taking on water first and foremost, then it wouldn't be buoyant at that point. And we also don't want dirt and water and grime getting inside of the boat and mucking things up. So on top of all of the main aspects here, one of the more detailed aspects we'll discuss is how we want to go about sealing up the boat. We'll touch on that a little bit here and then more in the next episode when we get into the details of the CAD. But this, at a high level, is what we want to build. So there's a few design challenges we'll have to tackle when it comes to the Benchy. First and foremost is seaworthiness. So the Benchy looks like a boat, right? However, as an actual boat, it's not very good. I think if you remember back to the last episode when I tried to dump the large Benchy I had in the water, one, it was barely buoyant, and two, it pitched forward rather steeply because of how nose heavy it was. So we're going to have to make a few changes to the design of the Benchy in order to make it a good seaworthy boat. So let's look at one of the first things we'll have to work on, and that's the position of the Benchy's center of gravity. Again, if its center of gravity is essentially the average of all of the mass on the boat. This is probably a little exaggerated, but I'm expecting that, based on what we saw in the last episode, we know that the center of gravity on the Benchy is, first and foremost, a bit forward, which causes it to pitch forward at the nose. It's also high, which makes it unstable. It will not hold itself upright when we try to place it in the water. So part of the design challenge for this project is going to be to take that center of gravity and try to shift it. We want to shift it back towards the center of the boat so it doesn't pitch forward. It keeps an even line in the water. And we also want to shift it lower so that it is more stable. So again, shifting it backward. We know from when we first tried this out, it was very nose heavy and pitched forward. And if we shift it backward so that the center of gravity is over the middle of the boat, we should keep it at a very even pitch in the water. That's pretty straightforward. What is a little more difficult, especially for me to grasp as I tried to get through this, and something I hope to talk about and maybe do an okay job explaining, is more of the center of gravity with respect to roll. And this is something to do with the height of the center of gravity. So we want this ship to be stable in roll. That's back, kind of left and right in the screen here, looking from the front of the boat. So the first thing I want to cover is, as I went through this design, the first thing I thought of was intuitively where I thought the center of gravity should be to keep a boat stable. And that was actually below what we call the center of buoyancy. And let's take a step back. The center of buoyancy is essentially all of the portion of the boat that sits underwater, the portion of the hull that is displacing water. We know from Archimedes that the amount of buoyant force created is equal to the amount of water displaced by the boat. So you have a buoyant force created, and that buoyant force is actually located essentially kind of similar to the center of gravity. It's located at the average center of the displaced volume, right? So that's going to have a left and right position. Obviously we want to keep it on the center line of the boat, and it's going to have a height as well. So One thing we can think of intuitively is to have our center of gravity below our center of buoyancy. And what that would mean is that our center of gravity would essentially hang from the center of buoyancy, almost like a pendulum. So that if the boat were to roll, the center of gravity would want to then find the lowest, the lowest point with the least potential energy, and that would always be directly below the center of buoyancy. So that's a very easy and intuitive way to think about stability in terms of our buoyancy location and our center of gravity. What the problem this creates is that that is a very unrealistically low center of gravity we would be looking for. And it turns out, first of all, let's go for one more slide where we'll talk about this intuitive center of gravity location. Again, when we have that center of gravity below the center of buoyancy, if it is lifted in roll, it's always going to want, almost like a ball sitting over the top of a hill, it's always going to want to roll back down the hill and find that lowest point of potential energy. And that's where we would find stability from. We would, once the boat rolled and lifted that center of gravity up, it's going to want to just swing back down like a pendulum, back down to its lowest position, um, which is where the lowest potential energy is. However, there is another way to think about stability in terms of center of gravity and center of buoyancy, and that is relative to what we call the metacenter. I'm putting that in quotes. So, not being a naval architect myself, the concept of a metacenter was a little new to me, so I hope I don't butcher this explanation. I did read into it a little bit to try to understand it. If I've said anything wrong here, please point that out in the comments because I don't want to give you bad information. But the main definition of the metacenter is that when the boat rolls, okay, two things happen. Okay, our center of gravity stays in one location relative to the boat because that doesn't change. Our center of buoyancy may actually change a little bit. As the boat rolls in one direction or another, more of the hull is forced into the water, and that kind of brings our center of buoyancy either right or left relative to the roll. And if we take that center of buoyancy and draw a vertical line up to where it intersects the center line of the boat, that's our metacenter. What is important about the metacenter is that if the metacenter in this situation is above the center of gravity, our boat is stable. If it is below the center of gravity, our boat is unstable. Now, on the face, that is just a definition with no explanation. So I want to get in the next couple slides, we'll talk about that more. And the one way, again, looking at it from the unstable configuration, see, versus the stable configuration, we're looking at a low center of gravity compared to the center of buoyancy. So when the boat rolls, the center of buoyancy shifts out a little bit, it's cast upward, and then our metacenter is still above our center of gravity. If we have a very high center of gravity as the boat rolls, we're looking at a very similar situation for the center of buoyancy. But when we cast that line upward, we find our center of gravity above our center of buoyancy. So one way to kind of explain why it is important for our metacenter to be above our center of gravity as opposed to below it is to think about the rolling moment created on the boat by the center of buoyancy. So in both of these pictures, we're looking at, in this case, a case where the metacenter is above the center of gravity. So when we take the center of buoyancy and cast it upward, we would find the metacenter right about here. But we're not even thinking about the metacenter right now. We're just looking at this from rolling moments. In the unstable situation, we cast that line up and we find our metacenter below the center of gravity. But more importantly, in the stable situation, the force generated by the center of buoyancy, which is we cast it upward, creates a rolling moment that is to the right of the center of gravity. So in this situation on the left, our boat is rolling left. However, because our force created by the center of buoyancy is to the right of the center of gravity, it's creating a counter rolling moment to the left. So our boat's rolling right, and our counter moment is to the left. In this situation, we would consider the boat stable because, again, that rolling moment wants to work against the roll of the ship. In the unstable situation, where our center of gravity is above the metacenter, what happens is that as our boat rolls right, the line of action of the buoyancy force is to the left of the center of gravity, which means it actually creates a rightward facing or a clockwise rolling moment. The problem is this rolling moment is the same direction as the roll of the ship. So it's going to work to exacerbate the roll. It's not going to bring it back stable until the point where the ship essentially just keels over. So I hope that makes a little bit of sense. I can explain more if need be, but just think of it as if our metacenter is above the center of gravity, when we look at it, the geometry of that, it means that the force we're creating due to buoyancy is going to be to the right or left, depending on the roll. We'll look at that in another slide, but it's going to be outside of the center of gravity. And when the boat rolls in one direction, that's going to create a rolling moment in the opposite direction that's going to want to center the boat and keep it stable. In the unstable configuration, if our metacenter is below the center of gravity, what's going to happen is as the boat rolls, the rolling moment created by the buoyancy force is actually going to work with that roll, which is going to just exacerbate it and roll the boat over. So again, going back to the stable moment, or the stable configuration, we had a picture previously where, again, the boat was rolling right. Let's look at both cases. So let's first assume the boat rolls right. The rolling moment from the center of buoyancy then rights the boat, but let's say it overcorrects and rolls left. Well, what's going to happen is that as that boat rolls left into the water, it's going to force more of the left side of the hull in. It's going to into the water, shifting the center of buoyancy over to the left, again outside of the center of gravity, creating a new counter rolling moment that's going to roll against this new roll of the boat. So think of the boat kind of just like bobbing back and forth. Every time it shifts in one direction, the center of buoyancy shifts outward of the center of gravity, creating a new rolling moment that's going to want to right the ship. So that's what we want in this situation. Because again, it's going to be very unrealistic to bring the center of gravity low enough so that it's below the center of buoyancy, but we just want to keep it low enough so that it's below the metacenter of the ship. And that should keep our ship stable. So a few ways we'll go about doing that are we'll tweak the geometry of the ship to try to bring the mass a little bit lower. I think some of the mechanisms we're going to put into this ship are also going to drag the mass a little bit lower. And finally, worst case scenario, we can also look at ballasting the ship a little bit just to bring that weight a bit lower. And again, so those two types of stability we can get out of this. In the case where the center of gravity is below the center of buoyancy, I would consider that a static stability, where there is a point of lowest potential energy that the boat always wants to keep at. Now, this will be a great thing to have, but it's an unrealistic situation because we need to bring a lot of mass very low in the boat. On the other case, with the metacenter, we have what I'd call dynamic stability, where the geometry of the ship is constantly creating new rolling moments that act against unstable orientations, keeping the ship centered. So I hope that explanation was clear enough. The other thing we're going to have to look at is essentially the buoyancy of the ship. The Benchy is not a very buoyant ship. It sits very low in the water. It does not displace a lot of water. It cannot carry a lot of load. So spoiler alert for, because I'm actually pretty deep into the CAD for this at this point. What I found is that I originally recreated the Benchy very close to the original design, put all the mechanisms in there, got a weight for the ship, and then did a little bit of stuff in CAD to get the buoyancy of the ship, and found out that it weighed 3 times more than the amount of buoyancy it generated. So this was a plan I already had considered, where we're going to have to change the profile of the Benchy a little bit in order to make it buoyant enough to hold itself up in the water. So again, that kind of, it's not great because we're going to have to change the existing outline of the Benchy, which you see in the red dotted line here, to something a little more bulbous, higher walls so we can displace a little more water. But what I do hope is that in the end, this still keeps very close to the spirit of a Benchy, only looking slightly modified compared to the original, while again, making the boat much more seaworthy. You kind of see, again, if you look at these both in side profile, you can tell it's different. Obviously, it's not as stark and sweeping and dynamic as the existing Benchy, but it still has the spirit. It's still mostly there. There's a little more bulbous and a little more actually seaworthy compared to the real life Benchy. And again, looking from the front, I'd imagine a situation where in the final outcome, this is actually even more aggressive than what's shown here. But we'll have to widen out this hull a little bit to make it more voluminous in order to displace more water. And it's a comparison between the two. The other thing we can look to add here, and again, spoiler alert, it's already been done, is to add a ballast keel to the boat. So again, the Benchy has a flat bottom for printing, obviously, One thing I want to do to take advantage of that is make a separate part that is the keel of the boat that has I think this is called a sail keel, I don't remember, but a very deep keel that can can be used to increase the amount of water that the hull displaces, and also give us a little bit of option to add a little bit of trim ballast. We can use that trim ballast to both set the height of the ship in the water, essentially, and also to adjust its pitch if need be. The draft of the boat. There we go. This is the term I was thinking of. So again, we can take the existing position of the benchy, a little bit nose heavy, and definitely we'll call it a little deep in the water. Use that ballast keel to increase its buoyancy and also to trim it so that its pitch is horizontal, is even. Another thing that'd be useful about a ballast keel is to add I think it's a sail keel. Correct me in the comments. I'm sorry if this is wrong, but we essentially add a large, broad, flat surface to the bottom side of the keel. What that's going to do is that if the boat is rolling, if the bottom of that boat was streamlined, it's going to cut through the water very easily, meaning we're not going to get much resistance against the roll. However, if we add a large, flat surface on the bottom of it, as the boat rolls, that keel, that large keel that juts out underneath of it, can actually create a good bit of friction force that would resist the roll of the boat. So we get a little bit of extra resistance against roll, and we get extra volume for both buoyancy and trim ballast if necessary. So that's why when you see some pictures of this in the future, we'll see we have a pretty deep ballast keel added to the boat. Probably butchering some terms here, and I apologize for that. So that ends the discussion on seaworthiness. The next thing we'll have to talk about is the construction of the boat. So the part breakup for this that I've determined is that we're essentially going to make the hull and the superstructure two separate parts. The hull will be nominally hollow with just the walls in there. We'll have some adjustments to the walls for sealing purposes, and then we'll have all of the points that the gearing of the wind-up mechanism will go into. So looking at this from a breakdown, with the wind-up mechanism will go inside the hull. The superstructure with the deck of the boat will go over top of that. Those will be screwed together. That'll create one sealed boat with a wind-up mechanism inside of it. The mechanism overview, so a little more detailed here. Starting from the top, we'll have an input handle. I like these spoiler alert. I like these large round handles. They have a nice old school feel to them. So this is something I like to design in. From the input handle, we'll have a shaft that runs down, and this is actually really cool. I'm able to use the chimney of the boat as a bearing for this shaft. So as this shaft will run down the chimney, which has been extended all the way down to the deck, creating a very long bearing surface for the handle shaft. That's going to go down to what I call a bobbin. That bobbin will be right in line with a flat wind-up spring. And what's going to happen is, we'll see in the next slide, that spring will actually be spooled off of its existing holder onto the bobbin as we crank the handle. And then when we release the handle, it's going to want to spin the spring off of the bobbin, and that'll turn the gear train out to the propeller. The gear train as designed is a 3-step gear train. There's a large gear connected directly to the bobbin. That goes to the first stage of the gear train, which is a small gear connected to a larger gear. That does the next stage of the gear train, which is essentially the same, except our larger gear is actually a miter gear, a bevel gear. There's a small difference between the two of them. That actually runs the gear at a right angle to the propeller. So again, for a more detailed look at the mechanism, we have, again starting at the top, the handle input that's coming down a rod that connects to the bobbin. Now, hopefully we want to seal that rod so that we can't get water down through that connection into the mechanism. That bobbin, if you look at a detail up in the right corner here, essentially is right in line with our constant force wind-up spring. So what happens here is that this hole in the spring will be connected to the bobbin, and as we turn that handle, the spring will be spooled up onto that bobbin. And when we release, it's going to want to pull itself back off of that bobbin, which is going to create our rotation that drives our gear train and eventually our propeller. These are called constant force springs because, again, they're very tightly wound, and the force they generate is just proportional to essentially the radius of the spring, which doesn't change much as you reel this out. So these are really good because instead of like a normal spring where we have that force that's proportional to the deflection, here we get a almost constant force all the way through our windup. I'm targeting at least two different variations for this spring, a 1.6 pound and a 2.6 pound spring for this. I want to be able to drop either in. They're roughly the same size. We can try out and see which one feels the best and gets the best results. So again, we wind up that bobbin, which will spool our constant force spring onto it. That bobbin is connected to the first drive gear. What I wanted to do here was have this gear be ratcheting, where as we wind the boat up, we won't drive the gear train. Only once we release the handle and want to drive the gear train do we actually get this gear to turn, which drives the rest of the gearing. One spoiler alert here, there just isn't enough space to do a ratcheting mechanism at the moment, so that has been left out in the first version of this design. So, can't get everything you want. In the end, I need to get this built and actually complete it. I don't want to spend 3 months designing it. So once we actually release that handle and the bobbin starts to unwind, we will directly drive the gear down here, which then, that's part of gearing stage 1. So we have a large gear to small gear that will essentially be stepping up the rotations of the handle from the large gear to the small gear. Connected directly to the small gear on stage 1 is another large gear, which drives a smaller gear. So we have another stage of increases in revolutions. And finally, in our gearing stage 3, our bevel gear, we will we have at least a 5-to-1 ratio here. So I don't have the exact numbers, but we should be looking at a several dozen to 1 ratio of input turns to output turns. So if we turn that handle 3-4 times, we should get hopefully close to 40, 50, 60 rotations on the propeller at the output, maybe even more. I'll get the exact number in our next episode when we discuss the outcome of the CAD and some of the details of the design. The final thing to discuss about the mechanism is speed governing. So if you compress a spring and release it, it's going to want to release all that energy as quickly as physics will allow, right? It's just going to pop back out. And the same thing goes for constant force springs. If you unwind them really long and almost like a roll of tape and let go of them, they're going to want to spring back as quickly as possible. So we need a way to slow that speed output down. And there are plenty of ways this are done in other mechanisms. One interesting way to think about this is like the escapement in a clock. As you wind that spring up and release that energy, you need a way to essentially slow that output into a tick-tock motion that can actually, run the second hand on a clock. That's done through the escapement mechanism, and it also uses, in some cases, a pendulum in order to govern that motion. I might be a little off base in this explanation here, but I think we're pretty close. One difference there is that essentially uses the geometry of the escapement to stop the rotation, and then, move back and let the rotation move again. In this case, with our speed governing, what we're going to want to do, or what we're going to rely on here, is actually just drag to govern the speed of the boat. I'm going to put a link to a favorite engineering channel of mine that actually discusses it very well, a breakdown of a wind-up toy, one of the little wind-up ones that plays music. And in part of that video, I suggest you watch the whole thing, but about midway through, they discuss how that mechanism actually governs its speed. And what they use is essentially just 2 flat paddles on an arm that are connected to the drivetrain of the mechanism. Those paddles spin very quickly. They're geared up very high. And the air resistance, or the drag created by those paddles, actually hits a point of equilibrium with the mechanism that actually losing the point here, that essentially slows the speed to a constant speed, or constant output speed that is lower than what it would have been had there been no speed governing in the gear train. So we want something like that. We want to essentially install a paddle onto this wind-up mechanism that is going to work against the fluid and use that drag created by the fluid in order to slow the output of this gear train down. And as luck would have it, we actually have a paddle built into this design already. That's the propeller. So the propeller is actually going to act as our speed governor. And one way to look at this is that the drag created by a fluid at low speeds, it's proportional to just it's the equation we see above. It's proportional only to some constants that depend on the fluid and object properties, and the speed of the object relative to the fluid. At high speeds, and we will be working at pretty high speeds relative to the fluid here, our drag force is essentially what we see here, negative 1/2 c rho a v squared, where c is a drag coefficient that's directed by the geometry of the object, rho is the density of the fluid, a is the cross-sectional area, and v is the speed of the object relative to the fluid. So at high speeds, the drag we create is proportional to the fluid density and also the square of the velocity. So our propeller is going to be running at pretty high speeds, so we're going to get a lot of drag created by it. And more importantly, in the case of, you'll see if you go to that link in the description, the case of that wind-up music box, those paddles had to work against the air. And in order to get enough drag against the air, they needed to move very quickly because, again, air is low density, so you need to spool those up with something like 3,000 RPM in order to create enough drag in order to actually slow the output of that music box, so that you can actually time the little fingers that are being driven to actually play the music. In our case, we get a little bit lucky here because we're not outputting that propeller into air, we're actually outputting it into water. And water, if you look down in the corner here, is roughly 1,000 times denser than air. So just by the design of this boat, the fact that it's going to be placed into water and our propeller is designed to drive against that fluid, that water, we're going to get a good amount of speed governing already built into this design. One thing I was able to test against was, if you remember in the previous episode, I showed off an off-the-shelf wind-up little boat. I think it was a little submarine with a monkey driving it. It's really cute. And when you actually pull that handle, or pull that string and release it, if you release it with the boat out of the water, it takes only about a second or two for the energy to be released. The propeller spins very quickly, and then it's over. If you place that boat into the water, it actually takes closer to about 8 to 10 seconds for all that energy to be released, because again, the propeller is spinning fast enough that it's creating a drag force in the water that essentially reaches a point where it hits an equilibrium with the force that's driving the propeller, and it doesn't stop it, it essentially stops it from accelerating. So we hit a constant velocity. That velocity is hit pretty quickly, and then we hold that velocity until all of the energy is spent in the system and the propeller stops. So that's how we're going to work on the speed governing here. We're going to rely essentially on the working fluid in that our boat is sitting in to be our speed governor. So we don't have to design anything else into it, which is great for me because I didn't feel like doing that. Final note about the construction, obviously, is that the hull in our design is going to be hollow compared to what it is in the Benchy. The Benchy essentially has the deck here. It angles up at the front for some reason. It's actually this extra bit of volume really makes it front heavy. In the construction we'll look at next week, this is actually hollow. There's a little bit of mounting points and some features built in for sealing purposes, but overall it's a hollow boat. That helps with weight, because it's the same amount of water displaced, but it's hollow. There's less weight inside of there. And finally, there's some printing considerations to take into account. So again, we're 3D printing this, and 3D prints tend to not be the most watertight things in the world. So there are a few things after researching that I came up with that can be tried, at least to try to improve the water sealing or the watertight capability of the 3D print. We can add extra perimeter passes, which is something I might play with. So that's as we go around the edge of the print, do we want 2, 3, 4, 5 perimeters before we get to the infill? We could try 100% infill. Spoiler alert, no we can't, because the boat will be too heavy and it will cannot displace enough water to hold itself up with 100% infill. We could try a little bit of slight over extrusion to kind of smush these layers together, and we could play around with the layer height. Again, mention in the comments if you know anything about this as far as watertight 3D printing is concerned. I've heard arguments for larger layer height and smaller layer height. I'm not sure which one would work better. I think intuitively lower layer height, but I could be wrong. And with that, we get to a spoiler for the next episode. So what you see here is actually the CAD output that I've managed to get to based on all of the design considerations we talked about today. Also shown here is that there was originally a version 1 CAD, and now there's a version 2 CAD. Again, this is, it's kind of nice going through all of this basic, high level concepting of these designs, and then trying to apply them as I actually work it in. Because what I found at the end was that once I was done designing version 1, almost ready to print and put it on the printer, I decided to take a check. I was able to, in the CAD, find out how much volume the hull displaces, essentially up to the line of the deck, right to the top of the propeller, and compare that to the weight of the boat. And as it turns out, and we'll talk about this more next week, it was displacing about 1/3 of a pound of water. So that's how much buoyant force we were going to create. The boat, however, weighed a pound. So the boat was 3 times heavier than the amount of buoyancy that it could create, which is a problem. It almost, pardon the pun, but it almost sank the project right there. But like we talked about in some previous slides, we can play with the geometry of this boat because, again, the Benchy is a very slim, slender design. It's a caricature of a boat. It's meant to look cool sitting on your desk. It's not really meant to function as a boat. So what I went ahead and did was I made the hull much more aggressive. It flares out a little bit, and we'll look at that next week. It's not as sweeping in the front as it was before. The keel that I added is much larger and more aggressive. And what we get from all of this is that for only a small increase in weight, we're able to triple the amount of water displaced by the hull in version 2 versus the hull in version 1. By tripling that amount, I'm essentially at a point now where I'm almost even with the weight of the boat. So I think I'm going to go ahead and try to print this out and see how it performs, and then see where I might have to cut down further if need be. But yep, that is, just wanted to talk about that now, because that is definitely a situation where the, these high level concepts about the stability of the boat, the buoyancy of the boat, they really do come into play. And when you're designing something like this, you got to keep these in mind. I got all the way to the end of my design, kind of assuming that this boat would have generated enough buoyancy to hold itself up, only to find out that I was off by a factor of 3. I needed to do some pretty deep changes in order to get this close to where I think it's going to work. So, take it from Bender here. The laws of science are a harsh mistress. So, yep, that kind of wraps it up for today. In our next episode, I will dive deeper into the SolidWorks CAD you saw in the previous slide. We'll get into a good amount of detail about the construction of the boat, the weight of the boat, how we plan to put it together, the details on the gear train and stuff like that. All of that is almost 100% decided at this point. I think by the time I am on the microphone talking about it, it might even be printed out, and we can even have a discussion about how it's working. So yep, I hope you enjoyed this. It's a half hour long. It's a bit of a ramble. I hope you learned a little something out of it. And like I say over and over again, if I was wrong about something, please correct me. I do not want to give people bad information. So looking forward to hopefully a few corrections there if I was wrong. But thanks for sticking around, and we will see you next week.